We will go over some example in energy conservation in this video. So let's start with the definition of conservative force. A conservative force means the work done by this force is independent of the path this object took, as known as object started from one initial position and end up with another final position. Doesn't matter which path it took, straight or go something like this, or any weird shape of path as known as start from position A, end up with position B. The work done by gravity is the same. Then we call gravity a conservative force. Now in this class, we have two conservative forces, gravity and spring force. All other forces we have in this class are non-conservative force. So let's using gravity as an example to illustrate conservative force and potential. So we define moving from position A to B, we define the change of potential energy, just a change of potential energy at the negative work done by conservative force. So in this case is gravity, by gravity. So you see apparently is mg hf subtract h0, and change of potential energy apparently is pf subtract PEI. So for gravity we have PE is mgh. So in this case, basketball drop from position A to position B is going down. This is displacement. Gravity is also pointing down. So gravity is doing positive work to the basketball, but its potential energy decreased. Now let's study mechanical energy conservation. So we have learned work and energy theorem a little bit earlier. Work, the total net work done on the system equals to the change of kinetic energy. This is work and energy theorem. So what happens if there is only conservative force doing work? Let's just using gravity for simplicity again. So what if only gravity is doing work to the system? Now make sure we stated it correctly. Only gravity doing work on the system. You can have other non-conservative force, but only gravity is doing work. Then the work done by gravity will be equal to the change of kinetic energy. And we also know work done by gravity is negative of changing potential energy from our definition, which means is negative of final potential energy, initial potential energy, equals KEF subtract KEI. So using this equation, after little bit rearrangement, we can have PEF plus KEF equals PEI plus KEI. So potential energy plus kinetic energy of the system is conserved if only conservative force doing work. If only conservative force doing work, we have potential energy plus kinetic energy is conserved always, and we give potential energy, so mechanical energy equals potential energy plus kinetic energy. Now let's try to look at a few examples that mechanics is indeed conserved. So let's neglect any non-conservative force, resistance, friction, air resistance. We assume all of that is zero. So apparently you see a projectile which is only has gravity acting on it. Projectile. Only gravity is acting on a projectile, so it has to be only gravity doing work to it. So mechanical energy has to be conserved for the projectile. Then the second case, a roller coaster, if we neglect friction, then for the roller coaster you have two forces acting on the roller coaster. You have normal force and mg. Now, however, if the roller coaster is always moving on the track, so its displacement is always along the track, the normal force by definition is always perpendicular to the track. So the angle between displacement and the normal force is always 90 degrees. Now, because work is F displacement cosine the angle between force and the displacement. If this angle is always 90 degrees, normal force doesn't do any work. So for the roller coaster, if we neglect friction, mechanical energy is also conserved. And now look at the picture on the right. This boy is swinging down. So when the boy is swinging here, you have tension, you have mg. Again, tension is perpendicular to the displacement. Always. Tension always perpendicular to the displacement. So tension doesn't do any work. Only gravity doing work. So mechanics is conserved for those three examples. So let's do first a quantitative example. You have a motorcycle driving down from a high place to a lower place. We want to find out what's its final velocity down here. So we know its initial height, final height, initial velocity. Now the motorcycle in the air would be just like a projectile, so only gravity is doing work on him, apparently. Mechanical energy is conserved, so we can build an equation. Final mechanic energy, which is final kinetic energy plus final potential energy equals initial mechanic energy equals initial kinetic energy plus initial potential energy. Now by solving it, just by solving this equation, we should have final velocity equals 46.2 meter per second. And this roller coaster, so we discussed the roller coaster, normal force doesn't do work, only gravity is doing work on the roller coaster, so mechanical energy is conserved, so you can build final mechanical energy plus final potential energy, and this HF is 10 meter, H0 is 18 meter, equals initial mechanical energy, and start from rest, so this term actually is 0. And by solving it, we should have final velocity is roughly 12.5 meters per second. Okay, what's happening if there is non-conservative force doing work in the system? We also start from work energy theorem. Total work equals change of kinetic energy. So total work, you can separate them into two terms. You put all work done by conservative force into this term, or work by non-conservative force into this term. So you still have work energy theorem, and you have your WC, work done by conservative force, equals negative of change of potential energy. And you find out you can have this. The work done by non-conservative force equals PF plus KEF subtract PEI plus KEI. So actually, the work done by non-conservative force equals to the change of mechanical energy of the system. And that's how we solve problems with non-conservative force doing work. So let's also do two examples. So you have two mass hanging like this. Let's call this one M1, this one M2. So M2 for 1.5 meters. After the for 1.5 meters, its velocity, its speed is 3.8 meters per second. Then what would be the work done by friction on M1, the 2 kilogram object? So the work done by friction should equal to the change of mechanical energy. So you need to find out the final mechanical energy of the system. Subtract initial mechanical energy of the system. And you have final kinetic energy of mechanical energy of the system. Let's first find out the final kinetic energy, which is 1/2 m1 plus m2 Vf squared. Final potential energy, which now you see m1 keeps moving on the platform, so m1 the potential energy doesn't decrease, only m2 its potential energy decrease by the amount of m2g 1.5 meter. So let's call this one hf, this h0. So pf final potential energy is m2g hf. Initial kinetic energy, which is 0. Initial potential energy m2g h0. And we have hf subtract h0 equals negative 1.5 meter. You put all the numbers in, you find that the work done by friction is actually 8 joules. Let's just do one more example. You have a car driving with speed 20 meters per second. Road is horizontal and straight, so there is no change in potential energy. There is a tree behind the car, so the driver brakes 20 meters before the tree. Coefficient of friction is 0.8. So determine whether the car will bump into the tree or the car can stop before he travels 20 meters. See, this is a car moving 20 meters per second, and you have a tree here. The distance D is 20 meter. You want to know whether the car can stop. So you need to find out magnitude of friction, which is mu k Fn, and Fn should equals to mg, so it's 0.8 mg. This is friction. So you want to know the work done by friction, which is friction times distance traveled. This is the work done by friction. Should equals to the change of mechanical energy of the system. There is no change in potential energy, so change in mechanical energy equals to change in kinetic energy. So you have 0.8 mg times d equals 1/2 mvf squared, subtract 1/2 mvi squared, and vi is 20 centimeter. No, 20 meter per second. Vi is 20 meter per second. D is 20 meter. G is 9.8. And we can eliminate F from each term because each term contains F. 1/2 Vf squared. Subtract 1/2 times 20 squared. If you solve it, you find your Vf is 9.3 meter per second. So the car, from the work done by the friction, the car still has 9.3 meter per second when it traveled 20 meters. So the car will bump into the tree. Hope those examples would be helpful for your exam 3, and good luck on your exam 3.